Digits line up hand in hand. Each step reduces till one shall stand. From many to one, the journey began. A triangle forms. Its sum is done. Welcome everyone. Today we will explore the beautiful problem called the triangular sum of an array. Let's begin with the problem definition. We are given an integer array where each element is a digit between 0 and 9. We repeatedly transform this array until only a single element remains. In each transformation, the new element at position I is defined as the sum of nums I and nums I plus 1 taken modulo 10. Our goal is to return the last remaining number after these transformations. Here are a couple of examples to understand better. If the input is 1, 2, 3, 4, 5, the output is 8. If the input is 5, then the output is 5 because a single element array is already its triangular sum. Let's walk through the example 1, 2, 3, 4, 5. First step we calculate 3, 5, 7, 9. Next 8, 2, 6. Then 0 and 8. Finally we are left with 8. So the triangular sum of 1, 2, 3, 4, 5 is 8. Constraints of the problem are as follows. The array length can be up to 1000 and each element is a single digit from 0 to 9. This makes brute force feasible since the maximum operations are manageable. A key observation is that this process looks very similar to Pascal's triangle. Each element in the final row can be represented as a weighted sum of the original array using binomial coefficients. However, since the input size is relatively small, a brute force solution already works well. Now let's discuss the brute force solution. We start with the given array and iteratively reduce it by applying the transformation. At each step, we update nums I as the sum of nums I and nums I plus 1 modulo 10. We continue this until the array size becomes 1. The time complexity is big O n squared and the space complexity is big O of 1 since we modify the array in place. Here is the brute force implementation in C++. The logic is straightforward. We run a loop while the size of the array is greater than 1. Inside, we update each element with its transformed value. Finally, we return nums 0, the only remaining element. Beyond brute force, there is an important mathematical approach using binomial coefficients. The triangular sum can be represented as a summation of combinations of n minus 1 close 1 multiplied by nums I taken modulo 10. This uses the connection between Pascal's triangle and the reduction process. This optimized approach has a time complexity of big O of n. It is faster for very large arrays, but given the problem constraints of length up to 1000, brute force is usually sufficient. Still, this insight reveals the elegant mathematical structure behind the problem. Let's compare the two approaches. Brute force is easy to implement, requires n squared time and constant space. The binomial formula method reduces time to constant big O of n, but the implementation is more complex. So brute force is practical here, while the optimized version adds theoretical beauty. To summarize the key points, this problem reduces the array step by step, collapsing it like a triangle. The brute force solution is more than enough for the given constraints, and the optimized approach demonstrates the deep link to Pascal's triangle. A real-world analogy for this process is a pyramid of stones. Layer by layer, the stones collapse until the single apex stone remains. The final stone is the triangular sum of the pyramid. To conclude, the triangular sum problem is elegant and insightful. From many numbers to just one, we see simplicity emerge from repetition. The brute force solution solves it efficiently, while the binomial theorem reveals deeper mathematics. Thank you for listening, and I hope this journey from many to one gave you both clarity and appreciation for the beauty hidden in arrays.